Random number generation in computer languages. This video is based on a research on the applications of random numbers and how to generate integer and real-valued pseudo-random numbers in different programming languages using their standard libraries. We have also done a small survey of the underlying algorithms used to generate random numbers in popular implementations of these languages. First of all, let's try to understand what randomness is. Randomness in computer science is a very useful concept. It has many applications in fields such as gambling, computer simulations in which involves in simulating various complex real-world phenomena, statistical sampling, which is selecting random samples from larger datasets, cryptography for generating data encryption keys, completely randomized design, and many other areas where random output is useful in producing an unpredictable result. When discussing single numbers, a random number is one that is drawn from a set of possible values, each of which is equally probable. For example, a uniform distribution. When discussing a sequence of random numbers, each number drawn must be statistically independent of the others. But how does predictable machines like computers generate randomness? Computers provide randomness via outputting random number. But again, how does a predictable machine like a computer generate an unpredictable random number? Computers use random number generators or RNGs to output random numbers. There are two types of random number generators: true random number generators (TRNGs) and pseudo-random number generators (PRNGs). In our research, we focused on pseudo-random number generators, but it'd be useful to have an idea about true random number generators as well, so let's take a minute and talk about how true random number generators work. True random number generators. In comparison with PRNGs, TRNGs extract randomness from physical phenomena and introduce it into a computer. You can imagine this as a die connected to a computer, but typically people use a physical phenomenon that is easier to connect to a computer than a die is. The physical phenomena can be very simple, like the little variations in somebody's mouse movements or in the amount of time between keystrokes. In practice, however, you have to be careful about which choice you choose. For example, it can be tricky to use keystroke in this fashion, because keystrokes are often buffered by the computer's operating systems, meaning that several keystrokes are collected before they are sent to the program waiting for them. To a program waiting for the keystroke, it will seem as though the keys were pressed almost simultaneously, and there may not be a lot of randomness there after all. However, there are many other ways to get true randomness into your computer. A really good physical phenomena to use is radioactive source. The point in time at which a radioactive source decays are completely unpredictable, and they can quite easily be detected and fed into a computer, avoiding any buffering mechanisms in the operating system. The Hotbit service at the Formobile in Switzerland is an excellent example of random number generators that uses this technique. Another suitable physical phenomena is atmospheric noise, which is quite easy to pick up with the normal radio. You could also use background noise from an office or laboratory, but you'd have to watch out for patterns. The fan from your computer might contribute to the background noise, and since the fan is a rotating device, chances are the noise it produces won't be as random as atmospheric noise. Thunderstorms generate atmospheric noise as well. Regardless of which physical phenomena is used, the process of generating true random numbers involves identifying little unpredictable changes in the data. The characteristics of TRNGs are quite different from PRNGs. First, TRNGs are generally rather inefficient compared to PRNGs, taking considerable longer time to produce numbers. They are also non-deterministic, meaning that a given sequence of numbers cannot be reproduced, although the same sequence may of course occur several times by chance. TRNGs have no period. Okay, that's it about TRNGs. As you can see, true random numbers are generated with the use of an external device connected to a computer. Let's now look at our key topic, pseudo-random numbers. Robert R. Coveyu of Oak Ridge National Laboratory once titled an article, "The generation of random numbers is too important to be left to chance." Pseudo-random number generators. As the word pseudo suggests, pseudo-random numbers are not random in the way you might expect, at least not if you are used to dice rolling or lottery tickets. A pseudo-random number generator is an algorithm for generating a sequence of numbers that approximates the properties of random numbers. The sequence is not truly random in that it is completely determined by a relatively small set of initial values called the PRNG state. Essentially, PRNGs are algorithms that use mathematical formula or simple pre-calculated tables to produce sequences of numbers that appear random. A good example of PRNG is the linear concurrential method. A good deal of research has gone into pseudorandom number theory, and modern algorithms for generating pseudorandom numbers are so good that the numbers look exactly like they were real random. Although sequences that are closer to truly random number can be generated using hardware random number generators, pseudorandom numbers are important in practice for simulations, for example, of physical systems with the Monte Carlo method, and are central in the practice of cryptography and procedural generation. Common classes of these algorithms are linear concurrential generations, lagged Fibonacci generations, linear feedback shift registers, feedback with carry shift registers, and generalized feedback shift registers. Recent instances of pseudorandom number algorithms include Blum-Blum-Sharp, Fortuna, and the famous Mersenne twistor, which is used in languages like Python. A random programmer once said, "Pseudorandom number generators vary greatly in quality. Some are horrible, some are extraordinary, but none are true." This humorous yet very true saying gives us a very good insight about pseudorandom number generators. Although pseudorandom numbers are being used for many purposes, careful mathematical analysis is required to have any confidence a PRNG generate random numbers that are sufficiently random to suit the intended use. In reality, most random numbers used in computer programs are pseudorandom, which means they are generated in a predictable fashion using a mathematical formula. This is fine for many purposes, but as we discussed, it may not be random in the way you expect if you are used to dice rolling and lottery drawings. How can we generate a pseudorandom number? You can create a formula that generates pseudorandom number. When designing the formula, the idea is for it to produce a string of numbers that would look random to anyone who did not know what the formula is. Characteristics of good formula include no repetition. The sequence does not cycle around and repeat itself. Good numeric distribution. If the formula is producing random numbers between 0 and 9, the numbers of zeros, ones, twos, etc. that it produces should be roughly equal over a long period of time. Lack of predictability. You have no way to predict what the next number will be unless you know the formula and the seed, the initial value. Here's an example of simple random number.